All right, so last time we took a look at this collapse of data from the Callister text. If we use this parameter C of equal to 20 in the Larsen-Miller, for the Larsen-Miller parameter. What we want to do this time is we'd like to come in and see if there's a way we can actually fit and find this value of C when it's not given. That would be like actually having real data, and you need to figure out how to collapse it. So we're going to go ahead and do that, and we'll fit this data that we had from the Callister text and see if we get a C value of 20 back. All right, so what we're going to do is we're going to be using the scipy.optimize, specifically curve fit, and we're going to be using the optimize command. So we're going to be using both of these now. So again, we wanted to define a function when we finally do get our collapsed data. We want to define a function to fit that data to a polynomial. So this is what we have here. I think last time we may have used A0, A1, and A2, now we'll just use B's. And we want to define now what is a cost function, at least something that we're calling a cost function. So we're going to use this optimize command, and this is going to allow us to come into a function where there's one value. In this case, it's going to be C for the Larsen-Miller value C, and it's going to change this until this function that I have here is minimized. Okay, so we're going to use an optimize and a minimization. So we want to minimize the return value from this function we're going to create, okay, by changing C. The rest of these are just the data sets that are given into the function. And what we'd like to return, if we're going to minimize this function, then we're going to return essentially the error between our fit and the data for a given value of C. All right, so first we're going to define a couple of parameters that I want to have available to me outside of this function. Normally, anything that's inside the function is unavailable on the outside. These are all considered local variables. Here, I want to make sure that my fit values and the data, my log sigma and my Larsen-Miller parameter, my data, is available once I run this function. So that's how we define those. We just call them global, and now they're active. They're no longer just local to this function. All right, so what are we going to do? We're going to go ahead and we need to convert our calibrated data sets into the Larsen-Miller parameter. Okay, we did this last time, except last time we had a C of 20 in here for all of these, right? And multiplying again by their temperatures. This time we're going to have our minimization function come in and change this value of C. Each time it comes in, it'll change the value of C. Then we'll get a fit to the polynomial. We'll see that below. And then it will check for errors between the fit and this data set. So as we get closer and closer to the correct value of C, where the data set collapses onto one curve, then our curve fit and our collapsed data will have the minimal amount of error. So that's the trick. All right, so once we get a guessed value for C, which is what gets input into here, we'll go ahead and do exactly like we did before. We'll append the data all together. I think last time we used horizontal stack. This time I just got the append function, so we're going to append, then append that one, and then append that one. Okay, so we put our data together. This is my X data, my Y data. Then we go ahead and zip them up just like last time. They're a list, and then we turn it into an array. And then we go ahead and sort by the X values. Okay. So at this point now we've got XY data pairs that are sorted according to the X. We'll go ahead and call the X log sigma data, and we'll call the Y values my Larsen-Miller parameter, values. So this is all identical, this part, to the last lesson, to the last video that I did. Then we have our curve fit. This is again the same as last time. Okay, we're going to get out these values for our curve fit, which is function. So that's these. So it's going to give us those values out. Okay, there's our function. And then we're going to go ahead and calculate the errors. We're going to calculate those by hand. So what we're going to do is we're going to get first what are called the residuals. And so this is going to be my y values for each data point. And then we're going to subtract off of those y values the y values I get from our fit. The function is our fit. And so the log sigma is the corresponding x values to these y's here. And we're going to put those into our functional fit using the B0, 1, B2, B3 that's contained in p-opt. So there they are. And so we'll calculate that. That's going to be the difference. Then we want to go ahead and square that. So we'll square these and sum them. So this is called sum of the squares. We want to do the square because this value here could be positive or negative. All right, the errors, and we don't care if it's below or above the line. We just want to know if it's deviating from the line fit. All right, so we have to square them, and then we'll sum them. Okay, and then we're going to go ahead and calculate the sum of the squares relative to the mean value of my data. So NP mean of my values. All right, so I got my parameter. I'm going to subtract off the mean, and I'm going to square that. This is like kind of getting rid of just a general error. And then we're going to go ahead and take these two values, the residuals minus this total, and we're going to then take 1 minus that. Okay, and this is referred to as the r squared value for the fit. Then we're going to return 1 minus the r squared value. Remember, the r squared value is good the closer it is to 1. We want to have a value here that we're going to actually minimize. So if we take 1 minus the r squared, this will minimize to 0 if r squared was to actually be a perfect fit of 1. So in the end, we're returning 1 minus this r squared value. And that's what we want to minimize. And so the program will minimize it again by simply changing the c. That's the only parameter in here that is available for it to actually change. All right, so those are my two functions now, a fitting function and this cost function where I'm going to try and minimize the error. And so now I'm going to go ahead and call optimize minimize. I'm going to minimize this cost function, so that calls my definition. It has one value that it takes, which is c, as one variable. These are fixed, these are data sets. So this here is the starting point. So it's going to use a c value of 1 as the starting point and calculate the error. And then it will change this automatically until we get a minimized function. The arguments that go in, that's just everything after the first value. So that's my variable, and everything else is called an argument. So here they are. These are my calibrated data sets that I'm going to put in. All right, then we're just going to print the result, and we're going to also print the values for the B0 to B3 fit. And then the result here is my value of C. Okay, right here. So result, once we do this, what we're minimizing is basically this value here. We started at 1, and then whatever it ends up being as a minimum, we're going to kick that out. And that is the first position in the X value in result. Okay, So let's go ahead and do that. I'm going to run it. And I get that my best CFIT is actually 20.789 instead of 20. That's pretty darn close, the textbook has. Let's go ahead and see what that looks like. So here it is. I've taken the log sigma, my x values. So this is my Larsen-Miller fit. I've put that in with my values for this fit, which is here, right? That's my polynomial fit. This is the data that it was fit to, so those are going to be my red points on here. And we will put in a title given the C value, which we said was result.x0. This is just formatting. So 20.789. And I can even put that right into my Y label, right? Since my Y label is C plus this log of the rupture time, I can put that straight in. So you can see it here is 20.789. All right, so that is a pretty good fit. And if we were to go ahead and use that example problem we had again, with now our new fit here for this 355 megapascal stress at 775 C, we would get a Larsen-Miller parameter of 21,097, setting it equal to this Larsen-Miller equation with our new C value here. And then we just go ahead and solve for the rupture time, and now we get 0.22 hours, which is actually only 36 seconds different from our last answer. So you can see where C of 20 is sufficient, as the textbook stated. All right, well, that is the fit. And so this is basically what you're going to do now with this set. This homework should be a little easier for you, I hope, in that I've pretty much have run through it and created everything for you. So, you have to update the data sets because you don't have these values anymore. So you can pick this one or this one, whatever one you want. And all you need to do is pull off the actual points on here. So you're going to have 550, 600, 650, 700, 750 as your data sets. So you need to update this again. And in your cost function, you want to also update here because you have one more value to go in now. You had 5 temperatures. So make sure you update these so that when you use this inside that these have the same name as what you're passing it. Okay. And you of course have to change the temperatures according to your data set. Otherwise, this function should run the same as we have here. You will have to update these names and these values here. Also, these names would have to get changed. So you do have some naming changes, but the bulk of this is just going to stay the same. Let's see what else. Yeah, I think that's about it. Oh, the global part. Yeah, don't forget the p-op won't change, so you can leave that. The log sigma, as long as you leave what we have here, that would stay the same. And then lm param is also. So I don't think you need to change the global values at all, just the names here and the temperatures and then what you're passing it. Okay. And then when you call your function, this optimize minimize, you'll have one extra argument here as well. So make sure you do that. This is the value of C. Again, the start, you can leave it at 1. You can change it to 10 or whatever you like. Just don't go too crazy. These C values are typically somewhere around 20. And then that should be it. And I haven't used this data set yet, so I don't know how that's going to work out. They should collapse, and it'd be interesting to see. If you're really feeling excited about this, you can take the data from both sets and see what happens. This is the same data. You just notice that the the pressure, the stress here is different for the two different regimes. Okay. All right. What else? So I think that's about it. Oh, let me just show you one more thing, I guess, real quick, because I know that this thing here, this star p-opt, is sometimes confusing, and we don't need to, I guess, make this confusing. So let me go ahead and just show you what p-opt looks like. So here it is. It's an array, and it has these three values in it, right? Which were the B0, B1, B2, B3. And our LM function, again, just grabs those. Hang on. Okay, so let's see, p-opt. So we have these values here, and actually I shouldn't have called LM here. It's exactly the same function, but in this particular run that we did, we actually just called it FUNC. That's right here. Last time I called it LM, and I'll probably go back and change this and make this LM, but we actually just called it function. This is the polynomial fit. Okay, but those are the values that go in. Here's what my p option looks like. And so instead of calling this plot function like this with a special star, what we could do is just go ahead and put in, let's see, p-opt, and we can go ahead and put in position 0, and then p-opt position 1, p-opt, if I can type, p-opt position 2, and p-opt position 3. And so there it is. So again, this is the shorthand here with the star p-opt, right? It automatically, instead of taking the list version, it just takes the values and strips these two list brackets off, so that what it gets put in is exactly what I've done here, but manually. Or you can do it like this if this is a lot clearer and easier for you. So I'm just putting in the 0th or first value, 1 index, that's a second index, that's the third value, the third index is the last value. So you just put them in like that. All right. So either way. All right, I think that's it. So just let me know if you have trouble dealing with these, but I think you'll be fine.